Good morning and afternoon to everybody. I am Ivan from Brno University of Technology, and I would like to present CoinWatch, which is a clone-based approach for detecting of vulnerabilities in cryptocurrencies. This is a joint work with Chinche, Weiyin, Xiaoying, and Latasha from SUTD, Yunlin from NUS, and Sunjun from SMU. So the motivation for this work are code clones which exist in cryptocurrencies. And what is the difference between code clones of, of other projects? There is a vast number of the clone projects. There is a high similarity of code bases of this clone project, and cryptocurrencies also suffer by high financial impact of unpatched vulnerabilities that are propagated among the clones. So we would like to have a mechanism to watch cloned cryptocurrencies. As an example of vulnerability, we select CV from 2018, which occurs due to reachable assertion weakness, and it can cause crash of any full node upon receiving an invalid block which double spends. It was already fixed on 18th of September 2018. However, there are still many cloned cryptocurrencies vulnerable. On the left side of this slide, we can see assert, which is present in the source code of the full node from this vulnerability. And the right side, we can see a list of cryptocurrencies which were cloned from the Bitcoin and the period during which they were vulnerable. We can see that some of them were not fixed even until the time of writing of this paper. Therefore, we propose a CoinWatch as a monitoring tool for such cloned cryptocurrencies, which would act as follows. Upon the new vulnerability occurs in the parent project, it is necessary first to parse CVE, then identify bug introducing and fixing commits in the parent cryptocurrency. This would require some annotation of a particular code representing the vulnerability and the fix. Then it would be necessary to match vulnerable code with child project, and finally report potentially vulnerable child project that don't contain the fix but contain the vulnerability. To set up such an approach, there is necessary to build a mapping of parent to child project, download the code bases of all child projects, and keep monitoring the CVs of the parent project at the National Vulnerability Database, as well as updates in the code bases of all projects. So now I will go over the particular steps of CoinWatch. First of them is CVE parsing, where several fields of CVE are extracted and parsed. For example, the date of publishing the vulnerability, the keywords extracted from the description of the CVE, then links to the version control systems like issues or pull requests which are related to the particular vulnerability, list of known cryptocurrency projects that were affected and their versions. The next step is code evolution analysis, in which the parent project is analyzed. In particular, we iterate over all issues of the parent project that are present in the parent project, and we go over all the commits and do the regular expression matching on the keywords extracted in the previous step. We save all the bug fixing commits which fix the vulnerability. And then in the next step, we need to identify the bug introducing commit. For this purpose, we are using the functionality of the key blame, which takes as an input the bug fixing commits. For the discovering to bug, on the discovery of a bug fixing commit, we are using SZZ algorithm, which is a state-of-the-art algorithm proposed in 2004. And as a result of this step, we have a bug fixing and bug introducing commits. These are used in the next step, where they are manually annotated. However, this step required understanding of the cause of the vulnerability, Therefore, it is non-trivial and it must be done manually. On the other hand, it's just a one-time action, and it should be done only once per one vulnerability. The result of this step is a detection test, which is obtained from the vulnerable code annotated, and this kind of detection test is suitable for the clone detector, which will be in the next part of the next step. But before this, it is necessary to filter the monitored project of our database, and we use the date of the forking to filter only project which might be vulnerable. We iterate over all the projects from our database, and we check whether the fork date is later than the minimal date of all bug introducing commits, and earlier than maximal date of all bug fixing commit. In this way, we try to identify the highest or the biggest set of the potentially vulnerable projects. So we employ this kind of conservative approach. If we already filtered the set of monitored projects, we pass them into the clone detector, which inputs the detection test as well, and it tries to identify the potentially vulnerable project using its clone detector. There might be a different clone detectors. Some of them might support type 1 clones, type 2 clones, or 3 clones. In type 1 clones, we account only for comments and white spaces, which may differ among the clones, while in the type 2 clones, there might be renamings of the variables and change data types. In the type 3 clones, there might be addition, deletions, and modifications of the code. So, we evaluated our approach using the Simian, which is type 1 clone detector. And as an input set, we used CoinGecko.com, which we parsed on all C++ GitHub project. In the result, we found 1094 GitHub repositories. On the right side, we see that there are also other projects written in other programming language than C++, abundant in the CoinGecko.com. And we formulated the 3 research questions, which should investigate the clone prevalence, accuracy of CoinWatch detection, and true positives and false positives. So the first research question tried to investigate the prevalence of the clones among the cryptocurrencies, which we already mentioned in the motivating slide, and we selected the 14 cryptocurrencies from top 50 according to the market capitalization, and we found out that the average clone ratio was equal to 30%. In many cases, this ratio was even higher, for example, 90%, and therefore we supported the positive answer on this question. And in the table below, we can see in a bold highlighted the version of the bitcoins which are most similar to the particular cryptocurrency project. So this gives us an intuition from which version this project were forked or which version they are based on. On the other hand, there are also some projects which don't have almost no code cloned, like Monero or Electroneum EOS or Steam. Our second research question focuses on accuracy, and we ask in it whether CoinWatch can accurately detect propagate vulnerabilities through clones. So the answer is positive, since we managed to find 384 vulnerable projects containing almost 800 vulnerabilities, so some of them have more than one vulnerabilities. In the result, we successfully filed 4 CVE extensions, and as a case study, we continue in CV 2018, which is the result of reachable assertion weakness that I mentioned before, and we monitored the number of unfixed cryptocurrencies over time, and 1 month after the disclosure, there were still over 30 unfixed projects. In February 2019, there were 9 unfixed, and at the time of writing this paper, there were still 4 unfixed projects, while one of them was already ceased. The third research question investigates the true positive versus false positive of the CoinWatch, and we ask in it whether is a clone without a fix equal to a vulnerability. This is translated to the reported vulnerability, whether is reported vulnerability equal to the true vulnerability. There are 2 ways how to analyze the answer on this question. First is manual investigation of the code from our patches, which is very time consuming. And the second one is checking with the developers and maintainers of the cryptocurrency project. We perform both of them, and the results are summarized in the table. We see the high true positive rate of CoinWatch. However, there were also some false positive. In particular, they occur due to alerting system enabled or presented in the code base of particular cryptocurrencies, but not references in the configuration. Therefore, the clone detector, Simian, reported this as a potentially vulnerable project because it didn't see behind the compilation. On the other hand, we also partially analyze the false negatives of the CoinWatch. The precise evaluation is very challenging because we would have to investigate all the cryptocurrency projects which were not reported. However, there are so many. Therefore, we sampled only a few projects and we found the true or false negatives in 2 cases. In a Bitcoin diamond, where was some new argument added to the function, which is a type 3 clone. We can see this in the below picture on the left side. And in the Bitcoin stash, when some function was renamed, this is the type 2 clone. None of them are detected by the CoinWatch. So this is one of the limitations that CoinWatch suffers only type 1 clones, and therefore this is sensitive to the false negatives. On the other hand, it's possible to use the type 2 and type 3 clone detectors within the CoinWatch, and this can decrease the false negative rates of the CoinWatch, but on the other hand, it may also potentially increase the false positive rate because there might be more projects matching the templates of the vulnerable code and the fixing code. Another limitation is a need for a manual annotation of the particular code in the bug fixing and introducing commits. However, as we already mentioned, it's just one-time effort per CVE, and we can watch thousands of cryptocurrencies by our tool. So in conclusion, we propose a CoinWatch as a monitoring tool for cryptocurrencies forked from parent project. We found almost 800 vulnerabilities in almost 400 projects. We reported 4 CVE extensions, which were confirmed by the developers and by NVD. And we argue that many attacks could have been prevented if CoinWatch was used to monitor this project in a very cheap fashion. So this is the end of my talk, and thank you for your attention. And if you have any question, I'm happy to answer them.